Hello everyone, I'm going to walk you through the combined cycle power plant energy prediction model. Let's get started. The goal of this project is to predict the net hourly electrical energy output of a combined cycle power plant using the environmental sensor data. This is a supervised machine learning regression problem because the output variables are continuous. Accurate prediction help improve efficiency and operational planning of the power plant. Below are the four ambient environmental variables used as a input features: temperature, ambient pressure, relative humidity, exhaust vacuum. These variables directly influence turbine performance. The target variable is net electrical energy output measured in megawatts. For the data, we have around 9,568 records of the environmental readings that are captured from the sensors at the power plant, and the data is split across 80:20 ratio for the training versus test data. For this project, I use linear regression as a baseline model due to its simplicity and interpretability. To capture more complex and non-linear relationship between variables, I also used a random forest regressor. Comparing a simple and an advanced model will help justify model selection. For this project, I choose Python as a modeling tool. While Excel is useful for simple regression, it is not well suited for advanced model comparison. Google AutoAM, although powerful, but act as a black box and limit interpretability. Therefore, I have used Python to have a full control over the modeling process and for the easy comparison of multiple algorithms. Now let's talk about the feature importance. Using random forest feature importance, we observe that the exhaust vacuum and the temperature have the highest influence on power output. Similarly, in linear regression as well, the feature importance, which is derived from the model coefficient, we observe that the ambient temperature has the largest negative coefficient, meaning that the temperature increases, power output decreases significantly. This aligns with the real-world problem behavior, where higher ambient temperature reduces the turbine efficiency. One limitation of linear regression is that it assumes a linear relationship, which is why we later compare it with the random forest model. This plot shows a strong negative relationship between ambient temperature and power output. As temperature increases, the efficiency of the power plant decreases, resulting in lower electrical output. I evaluated model using RMSE, which is root mean squared error, and R square. Root mean, root mean squared error tells you on average how far my prediction is from the true value. It is expressed in the same unit as the target variable, which is megawatt here. Lower the value, the smaller are the prediction errors and the better is the model. Squaring penalizes the error more, large error modes, which is important in this case where the large prediction errors are costly. R square answers how well does the model explain changes in power output. If the value is 1, it means it's the perfect prediction. If it is 9.95, it means the 95% of the variation is explained in the model. Now in the random forest, as you can see in the numbers here, it makes a smaller prediction errors and explains the more variability in the power output. Therefore, it has a better accuracy, and that is why the final model chosen is the random forest, which has a higher R square value and lower RMSE value. This plot compares actual power output with the predicted output for both linear regression and random forest model. Ideally, all the points should lie on the diagonal line, which represents perfect prediction. We observe that the random forest model produces predictions that are much tightly clustered around this line, indicating higher accuracy and the lower error compared to linear regression. So this visual supports our quantitative result wherein the random forest achieved lower RMSE and higher R square. Next is the demonstration of the final random forest model by providing example of the environmental condition wherein I have used these numbers for the 4 input variables, and the prediction is being computed as around 454.97 megawatt by the random forest model. Hence, it's concluded that a random forest better captures the non-linear relationship between environmental conditions and power output. Hope you like this video. Thank you.